What if, instead of teaching an AI to guess just one single word at a time, we force it to predict multiple words all at once? Well, the data suggests this one tweak dramatically improves both the efficiency and the actual reasoning capabilities of large language models.
To really get why this is such a breakthrough, we kind of need to establish our baseline. Right now, the state-of-the-art models you're probably used to, like GPT or Llama, they learn through a process called next token prediction. Think of it like a driver navigating a super winding road at night, but their headlights only illuminate exactly 1 foot ahead of the car. Sure, they can stay on the road by making constant, tiny little corrections, but they can't effectively plan for a sharp turn 50 feet away. Standard AI training rewards the model purely for guessing that single next word, which just forces it to hyperfixate on immediate local patterns rather than seeing the big picture.
The next token bottleneck, and how it overlooks the hard decisions.
There is a pretty glaring inefficiency in modern AI training known as teacher forcing. We literally have to feed these models orders of magnitude more data than a human kid needs just to reach basic language fluency. And the core issue is that standard language modeling losses create this massive bottleneck. Because the AI is only graded on the very next word, it inherently prioritizes short-term rote memorization over actual strategic planning. It gets incredibly good at short-term syntax, but it totally overlooks the long-term semantic dependencies and those hard decisions that actually define the structure of a paragraph or a complex block of code.
Moving to Section 2, the multi-token solution. This is a real paradigm shift. So if looking just one step ahead is the problem, this multi-target prediction architecture is the fix. Instead of a single, narrow path to a single word, picture a shared trunk that represents the model's core understanding of the context. Branching off that trunk are n independent output heads. In this specific setup, imagine 4 distinct output heads all operating in parallel. At every single position in the training data, the model is being asked to predict the next 4 future tokens simultaneously.
Section 3. Memory and Inference Architecture. Now, if you know a bit about machine learning, a giant red flag might be going up in your head right about now. Wouldn't predicting 4 or 8 tokens at once just absolutely fry your GPU memory? Well, the researchers engineered a brilliantly memory-efficient implementation to solve this. First, a forward pass goes through the shared trunk. Then, they sequentially compute the forward and backward passes for each independent head one by one. They accumulate the gradients down at the trunk, and here's the real magic trick, they free up the memory of the logits from the first head before ever moving on to the second. Basically, they avoid materializing all the predictions in memory at the exact same time. By sequencing those passes, the peak GPU memory utilization drops dramatically. Instead of multiplying by n heads, which, by the way, scales terribly across massive vocabularies, it completely drops back to the baseline cost. It essentially requires the exact same peak memory as standard training. This clever bit of engineering means we can do multi-token training with absolutely zero overhead in training time.
All right, Section 4, experiments on scale and speed. Theory and architecture are cool, but the real data here is just striking. The team trained models ranging from 300 million all the way up to 13 billion parameters. For the smaller models, multi-token prediction doesn't actually do a whole lot, but as the model scales up, the benefits absolutely explode. Just look at the 13 billion parameter model. Using the exact same computational budget and training data, the multi-token model solves 12% more problems on the HumanEval coding benchmark and an impressive 17% more on the MBPP benchmark compared to the standard next token model. That's a massive leap in capability. And the crazy thing is, the benefits aren't just in accuracy, they're in speed. Models trained with 4-token prediction achieve up to 3 times faster inference speeds. Since the model has already been trained to accurately predict multiple steps ahead, it unlocks a super clever technique called self-speculative decoding. The model basically drafts a few tokens ahead using its extra heads and then verifies them simultaneously. This radically speeds up the text generation process even when you're working with large batch sizes.
So, what's the magic number, the optimal n? The researchers experimented with different values for how many tokens to predict at once. They found that for natural language and code, using your standard 32K vocabulary, predicting 4 tokens at once is right in the sweet spot. But if you strip away the tokenizer entirely and train the model purely on raw bytes of data, predicting 8 bytes ahead is optimal, and the results there are just wild. Multi-byte prediction solves 67% more problems than a next byte baseline, and the inference speedup jumped to an incredible 6.4 times faster.
Section 5. Fine-tuning and natural language. This research proves this isn't just some pre-training gimmick.
When they took a 4-token pre-trained model and fine-tuned it on the highly challenging code contest dataset, it consistently outperformed standard models. Interestingly enough, actually, this is key. The absolute best algorithmic reasoning performance came from pre-training with 4-token prediction, but fine-tuning it with a standard next token loss. It seems like the super-rich representations it learns during that multi-token pre-training provide a much stronger foundation for downstream tasks.
Now, to keep things totally objective, we have to look at where this method doesn't move the needle. When they evaluated it on static, standard, multiple-choice natural language benchmarks, tests where the AI just picks A, B, C, or D, the multi-token models showed flat or even slightly degraded performance. The researchers make a fair point, noting that simple multiple-choice tests probably just aren't suited to capture the true, complex capabilities of this specific training method. Because where this model truly shines is in generative excellence. When it's asked to generate abstractive text summaries for Rouge benchmarks or solve step-by-step natural language math problems on tests like GSM-8K, the multi-token models consistently blow past the baselines. The real power of this architecture is unlocked when the AI actually have to construct and plan out what it's going to say. Finally, Section 6. Why does it work?
So what's the underlying theory driving this huge boost? Think about how a typical sentence is built. In any text, some words are just inconsequential stylistic choices, right? While others are critical choice points that completely dictate the structure of the sentence. Multi-token prediction implicitly assigns much higher mathematical weights to those hard-to-predict choice points. The model is penalized heavily if it gets those structural turning points wrong, which forces it to actually learn the underlying logic of the language.
Ultimately, this fixes a massive distribution mismatch. In training, models are traditionally spoon-fed the correct answer one tiny step at a time. But out in the real world, during inference, they have to generate text autoregressively on their own, where a small error can easily compound into a huge mess. By increasing the weight of mutual information between tokens, multi-token prediction bridges this gap. It quite literally forces the AI to care about the long-term structure of its answers, teaching it to plan ahead rather than just blindly reacting to the last word it spat out. Let's bring all this together and synthesize the key takeaways from this explainer. Multi-token prediction is a shockingly simple modification that dramatically improves both sample efficiency and reasoning. Thanks to some really clever sequential memory management, it costs zero overhead in training time. At scale, it unlocks massive gains in coding and generative tasks. Plus, it provides up to 3x faster inference speeds. But most importantly, it fundamentally shifts how an AI learns, pushing it toward long-term planning over short-term rote memorization. Which leaves us with a pretty profound question to ponder. For years, one of the biggest criticisms of language models is that they're basically just stochastic parrots, guessing the next word without any real foresight or understanding. But if multi-token prediction allows AI to actually look ahead, assigning weight to critical choice points and strategically planning its outputs before it even generates them, what does this mean for the future of artificial general intelligence?